We asked Dr. Christian Jeltsch to answer questions about battery electrode compounds. To begin, can you tell us something about the engaged materials and their functionality?
Sure. So talking about lithium-ion batteries, we are talking about the anode and cathode materials. The anode materials being carbon-rich materials, meaning graphite, for example, larger particles is the active material. There can be also carbon nanotubes or carbon black, conductive carbon black. On the cathode side, we are mostly talking about NMC, nickel, manganese, cobalt blends. That's also the active material on the cathode side. And the target here is to form a smooth, clean, homogeneous light layer that provides the desired electrical performance.
There is a series of requirements to the electrode performance where the processing step is equally important. Can you elaborate on the impact of the mixing step?
So the blending of the electrode materials is indeed very important in that sense that without a functioning electrode, the whole battery cell cannot perform. There's two essential criteria. One is forming a homogeneous layer, as mentioned before, and the other one is preserving the larger particle integrity, the geometry of these particles. Because the morphology of the final film is impacted by this particle shape, and that defines also the percolation pathways of the electrodes during the charging and discharging process.
What are the disadvantages of today's processes, respectively? Where lies the potential for improvements?
So currently, there's systems applied that either vary in shear or they are differentiated in being batch-to-batch or continuous. Batch-based systems may suffer from batch-to-batch variations, while continuous systems provide more consistency. On the other hand, currently used continuous systems usually apply relatively high shear, which might lead to particle grinding and the destroying of larger particles, as I've been mentioning for the active materials.
Which advantages of the Buss Kneaders are specifically matching the process requirements of battery electrode compounds?
The Buss Kneader combines the benefits of being a continuous system, and we are also able to adjust the shear gap to that extent that the larger materials of the active parts can stay intact and they're not grinded. This leads to performance stability and a very well-functioning, consistent, continuous process.
Looking forward, which trends do you see in the near future for battery anode compounds?
So the industry is clearly moving towards dry systems at the moment, meaning either reduced solvent content or completely dry systems by avoiding the solvent. The benefits are clear, it's more cost effective, has a low carbon footprint, and it's also safer environments for the production process. New formulations require automatically new binders, new materials, and the dry systems is also where we see explicitly our strength at Buss for battery research.
When supporting these trends, what does Buss offer to customers developing electrode materials?
We do have our customer trial center here, our test center. That's where we have run several trials with various cell manufacturers in the battery field for electrode materials. That's how we can support our customers internally. On top, we are collaborating with plant manufacturers to make sure that the Buss Kneader is perfectly compatible with the material handling systems in an industrial environment.
What are the next steps Buss wants to take in supporting battery developments?
So we are currently collaborating with several research institutes in order to strengthen our presence at conferences, but also at trade fairs to build the network. We are collaborating, as mentioned before, with plant manufacturers because we are thinking the whole chain from the unloading stations for the trucks via the processing step on the Buss Kneader to the calendaring step to be ready for the final cell assembly with our customers.
Special thanks to Dr. Krishan Jeltsch for the interesting insights into this field.